Hello! We are jumping into using our truth table knowledge today. We're going to be examining statements and figuring out whether statements are equivalent or trying to create equivalent statements. When we say equivalent, logically equivalent. Logically, they have the same meaning or the same truth values. Okay, so two statements are equivalent, and it's symbolized by this double arrow. But notice it looks a little different than the double arrow for biconditional. It's a little thicker there. If the final columns in their truth tables are exactly the same. So if you take two statements and set up truth tables for them, if that last column in each truth table matches up exactly, then you know that those two statements are logically equivalent to each other. You can take one statement and reword it as the other statement and still convey the same meaning. There are certain statements that we know are always equivalent. Just time and again they come up, they've been proven with truth tables. If it fits one of those forms, you can look at it and go, oh, I know that's equivalent without doing truth tables. Otherwise, if it's a less commonly used statement, less commonly used statements, you're going to have to do truth tables to try to figure it out. So let's look at an example where we try to figure out if two statements are equivalent or not. Let me change my pen color again. I keep forgetting that it keeps doing the default pen color is red, and I don't want to use red. Okay, so we have to decide whether these two statements are equivalent. Let's say we have the statement, if P then Q, and if Q then P. That looks familiar. That's the whole biconditional statement. Oh. P if and only if Q. Huh. We already know the outcome of this because we've done this before. Okay. Sometimes you look at it and you go, I know the outcome. I don't need to do a truth table. I can see that they're equivalent. But let me just quickly recap the truth table situation here with these statements. Starting with the first statement, we're just dealing with P's and Q's, so we'll do our initial standard setup. And in that first statement, we have two sets of parentheses we have to handle. And then after we handle those, we can do the and joining them. Okay, so if P then Q. Remember, if then is only false if you go T to F. T to T is true, T to F is false, F to T is true, F to F is true. Then if Q then P, T to T is true, F to T is true, T to F is F, F to F is true. And then the and statement, well, and they both have to be true, otherwise it's false. And there you go. Now for the other statement, I'm just going to kind of tag along with this truth table. I already have the PQ columns over here. We know that the biconditional goes TFFT because as long as both truth values are the same, it's true. If they're different, it's false. So those final columns for both of those statements are the same. And that tells us that we have equivalent statements here. So you can use that little double arrow with the double, it's like two arrows pointing in different directions. So those final columns are the same, then yes, they are equivalent. Okay. Now let's look at an example where they didn't come out to be equivalent. Just to show you, how that might work out. All right, let's say we have first statement. We're going to decide if this is equivalent or not. First statement is P or Q and R. Second statement is P or parentheses Q and R. So they look similar. They both are P or Q and R, but look, notice the placement of the parentheses. That makes all the difference. Okay, so we'll get started with our 3 columns here. Okay, so for the first one, we have P or Q. So let's do that. Or just one of them has to be true to be true. They can both be true to be true. So the only time it's false is if both are false. So T or T is true, T or T is true, T or F is true, T or F is true, F or T is true, F or T is true, F or F is false, F or F is false. And then we got to do P or Q and R. We already have the P or Q column right here, and then we got to do the and R. Remember, and they both have to be true to be true. So we got true, false, true, false, true, false, false, false. Okay, so this is the final column for that statement. Now again, I'm just going to tack on to that truth table to do the other statement. The other statement has parentheses Q and R, so we got to do that. T and T is true, T and F is false, F and T is false, F and F is false, T and T is true, T and F is false, F and T is false, F and F is false. And then we got to do P column or this Q and R we just did. And then or, just one of them has to be true to be true. Okay, so P column's way over here. True or true is true. True or false is false. True, not false. Sorry about that. Mine wandered a little bit there. Trying to focus. Unfortunately, my grandmother's in her final hours, so I'm trying to focus here, and I'm like, oh, I can't. All right, P or Q and R. Okay, let's do this again. True or true is true. True or false is true. True or false is true. True or false is true. False or true is true. False or false is false. False or false is false. False or false is false. Okay. These are not the same. So no, these two statements are not equivalent. The final columns for the two statements were not the same, so the two statements are not equivalent. And that's, if you're not sure if two statements are equivalent or not, this is what it comes down to. Just do truth tables and see what happens in those final columns. Okay, now let's look at some common statements that pop up that are always equivalent. One of those is De Morgan's laws. We talked about De Morgan's laws in the previous unit on sets. They looked a little different because it was unions and intersections with sets. It would be something like set A intersects set B complement equals A complement union B complement. That's what one of them looked like for set theory. And we set up Venn diagrams to show that, hey, they both use the same region, so they're both equal sets. Also, you had A union B complement equaled A complement intersect B complement. That was also with sets. But now, you have these two that have to do with logic. Notice the similarities. Instead of complement, you have the negation. And instead of the rounded symbol, you have the more pointy symbol. And instead of sets A and B, you have the P's and Q's. But the pattern's very similar. And with logic, to show that these statements are equivalent, you can use truth tables. So let's do that real quickly with De Morgan's laws. I like to look at this and think about it as like distributive property in a way. Like negation gets distributed to P, the and changes to or, negation gets distributed to Q, you know, everything changes. Or go in the other direction, it's like you're factoring out a negation. But anyways, let me do a truth table so you can see how this looks. Setting up our P, Q. Okay, parentheses here is P and Q. So P and Q is true, false, false, false. And then the negation outside the parentheses says take that result and negate it. So false, true, true, true. That looks like an F now because I messed up. Let me erase that and rewrite it as a T. Okay, so that's the final column for that statement. The other statement needs a negation P, a negation Q, and then a negation P or Q, or not Q. So let's take a look at those. Not P will be false, false, true, true. Not Q will be false, true, false, true. And then the or statement, just one of them has to be true to be true. So false or false is false, false or true is true, true or false is true, true or true is true. So notice final columns are the same. So that verifies the equality here. Okay. Now once you know that De Morgan's laws are like that, you can then apply them to scenarios without ever having to use truth table. For instance, let's say you're given this statement here. Negation, parentheses, negation P and Q. And you wanted to find a statement that this is equivalent to. Seeing the negation, parentheses, and then seeing the and here, that triggers my memory of De Morgan's laws. And remember, De Morgan's laws, it's kind of like distributive property. So what I can do in this scenario is I can distribute this negation. And I could say the negation of P, change the and to or, and negate the Q. But negation of a negation just cancels out the negation, so you're left with P or not Q. Like that. Minus that line that just drew through there. So that should be P or not Q. So it's logically equivalent to that. And if you want to test it, set up truth tables and do this statement and that statement, they will come out with the same final columns. But you didn't have to do anything with truth tables because you used Morgan's laws. What if you have something like P and not Q, and you want to figure out what that's equivalent to? Well, I see an and I'm like, well, De Morgan's laws, not only can I think about it distributing a negative, but I can also think about it as like I'm factoring a negative. So I can go ahead and take this statement and find something equivalent by doing negation parentheses, change the P to not P, change the and to or, change the not Q to Q, and there you go. There is a logically equivalent statement for you. just by using De Morgan's laws. And then set up truth tables for these two. Final columns will be the same. And don't let it throw you if they decide to put it in words instead of symbols. Let's see, what if they tell us the dog was not a bulldog, and the dog was not a boxer. Okay, the dog was not a bulldog. That's a lot like having a not P. Like maybe the dog was a bulldog is P. And the dog was not a boxer is a lot like having a not Q. Like the dog was a boxer could be Q. So by De Morgan's laws, I want to find something logically equivalent to this. I can factor out the negation, change the not P to P, change the and to or, change the not Q to Q. So I could say, it is false that, or it is not true that. And then P or Q. The dog was a bulldog. Or the dog was a boxer. And there you go. So you saying the dog was not a bulldog and the dog was not a boxer is logically equivalent to saying it is false that the dog was a bulldog or the dog was a boxer. So there you have it. Alright, a few more equivalences. These don't have real names per se, like unlike De Morgan's laws, but they are equivalences still. If P then Q is logically equivalent to not P or Q, so here's a conditional statement, and it has a disjunction that is a logical equivalence to it. Then you also have the negation of the same conditional statement. And it has a conjunction that's logically equivalent to it. So let's set up truth tables to show this. Alright, so we know that there's a conditional statement, if P then Q. We now know that there's a logical equivalence to that. That's the disjunction, not P or Q. And let's prove it by doing a truth table. Okay. If P then Q, that column is going to go TFTT. So the only time it's false is if you go T to F, otherwise it's true. Not P or Q. I need a not P column before I finish that one. 2 true, 2 false is now going to be 2 false, 2 true. And not P or Q. F or T is true, F or F is false, T or T is true, T or F is true. So final columns are the same. This verifies the logical equivalence. Now to show the other one, to show the logical equivalence with the negation, we don't actually have to do a truth table. We can apply De Morgan's laws to doing that. This equivalence statement, let's negate both sides of it. It's like an equation. Negate both sides, keeps it balanced. Alright, so we have the negation of the conditional here on the left, which is part of that equivalence already. But on the right, it doesn't quite look the same. Notice that we have a negation parentheses. So we can apply De Morgan's laws. Negation of the negation of P turns that into P, or changes to and negation of Q. So there's the other one. Negation of the conditional is logically equivalent to P and not Q. Didn't have to do truth table to verify it because we have De Morgan's laws. And that was the two right here that we were given earlier. Alright, let's look at an example where you have to do words to work with those. If Jeanette buys a new car, then she sells her old car. So if P, then Q. Okay? And we want to write one that's logically equivalent as a disjunction. So we're going to write a not P or Q. So Jeanette buys a new car is P. So Jeanette does not buy a new car is not P. Then instead of a conditional, we have an or. And then Q. She sells her old car. And now you've got two statements that are logically equivalent to each other. Let's say you have something like, I am cold, and the heater is not working. So this one's a P and not Q. You want to do something logically equivalent? You can do negation of if P then Q. So you could say it is false that, or it is not true that. It is false that if I am cold, because I am cold is P, then not Q is the heater is not working, so Q is the heater is working. I did not. I was writing. Why did it do that? Sorry. So it is false that if I am cold, then the heater is working. That's something that's logically equivalent. Alright, another set of interesting things to look at. Variations on the conditional statement. We've got the original statement, the conditional is if P then Q. The converse of that just reverses the order and says if Q then P. We dealt with the converse when we were playing with biconditionals before. The inverse keeps the order but negates them both. Contrapositive switches the order and negates them both. I have a little story to tell you to help you to remember what's what. But first, let's set up truth tables and show you what's what. Alright, let's start our truth table with PQ columns. Okay. Then we have if P then Q. That's the conditional statement. We know that that goes TF, TT. Okay. Then we switch the order. We do it backwards, and that's the converse of the conditional. Well, for the converse, if Q then P goes T, T, F, T. So these two are not logically equivalent to each other. They do not get the same columns in the truth table. Next one's the inverse. That's the not, if not P, then not Q. Well, not P is false, not Q is false. That would be true. Not P is false, Q is true. False to true would be true. True to false would be false. True to true would be true. Notice that these two come out the same. So the converse is logically equivalent to the inverse. Basically, if you switch the order and negate them both, you've got something that's logically equivalent. And then down here we got the contrapositive. Notice that we're switching the order and negating both from the original conditional statement. So what should happen is contrapositive and conditional should be logically equivalent. False to false will be true. True to false will be false. False to true will be true. True to true will be true. So yes, the conditional is logically equivalent to the contrapositive. Okay, little story, because I know when I first learned about these, I was like, contra what? I know the words were, first of all, kind of foreign, and then trying to remember what was really challenging. Conditional, for some reason, was easy, because I think my professor had talked about it so much, I was like, oh, if P, then Q, that's easy. But the others, well, contrapositive I quickly caught on to. I was like, contrapositive is a really long, weird word. And that's the one where we do the most to the conditional statement. We take if P then Q, we swap the order so it's Q to P, and we negate them both. So it's not Q to not P. So that, for me, stuck. Which one contrapositive had to be. But I kept reversing converse and inverse. I kept mixing those two up, but not sure which one was which. And I managed to memorize it to get through class when I was a student, but I didn't really have a good way to quickly remember it until my brother got married when I was an adult, like when I was actually teaching this class already. You might wonder how my brother's marriage had anything to do with this, but my brother and his wife had this big, elaborate Catholic wedding. When my brother and his wife met, he was Catholic, she was actually Mormon, and she converted to Catholicism, and then they both got married in the Catholic Church. So they had this big Catholic wedding. She had a big, beautiful dress. He had the fancy tux, all that stuff. So it was gorgeous. But the one thing that was backwards from this, something you would not expect from this big formal ceremony that lasted like an hour and these beautiful gowns and tuxes, was that the bride and groom wore sneakers, tennis shoes. But not just any tennis shoes, they wore Converse. Because my brother is a huge fan of Converse sneakers. He wore black ones that basically matched his tux, and she wore white ones that matched her dress, and she had them decorated with like lace and sequins and stuff. So yeah, it was cute. It was like her dress was long enough you didn't really see her sneakers until she was like dancing and stuff. But it was cute. It was a little backwards that they're wearing tennis shoes with this fancy outfit. And it was Converse sneakers. So from there on, I could remember I know it's weird to relate it to this, but I can remember that if I take the conditional statement and just do it backwards, that's my converse. And then inverse is the other one. You know, I can remember contrapositive because it's reversing and negating. It's a long process, long word. I can remember converse because it's backwards, like wearing sneakers at a fancy wedding. And then inverse, same order, just negating. I just need to remember inverse is that final one that I didn't have a clever thing to remember it with. And that's that. So I don't know if my story is going to help you, but if it does, great. If not, come up with your own story. Find a way to remember it, or find some kind of little trick. Okay, so let's wrap this up. Let's look at an example with some words where they want us to do some things. Let's say you have an initial conditional statement. If the water is running, then Linus is getting a drink. Oops. Okay, this is the original conditional statement. If P, then Q. And the exercise wants us to write the converse, inverse, and contrapositive of this statement in sentence form. Okay. So starting with the converse. Remember, that just switches the order of the antecedent and consequent. So we're going to have if Q, then P. So if Linus is getting a drink, then the water is running. Okay, these two are not logically equivalent. And if you kind of think about it a little bit, you'll see it doesn't make sense. The two don't mean the same thing. They don't make sense if you try to think they mean the same thing. In the first one, it's saying, well, the act of the water running follows up with Linus getting a drink. I'm picturing Linus seeing the water running, then getting a drink. Whereas the second one, if Linus is getting a drink, then the water is running. This one is like saying, well, Linus getting a drink is then, the follow-up is causing the water to run. Two different meanings. One of them, the water running, prompts Linus to get a drink. The second one is Linus getting a drink prompts the water to run. Two entirely different meanings. All right, inverse. Original order, but negated. Okay, if the water is not running, then Linus is not getting a drink. So converse and inverse logically equivalent. You know, if Linus getting a drink prompts the water to run, then we could safely say that if the water is not running, then Linus couldn't be getting a drink, because, you know, if the prompt of Linus getting a drink isn't happening, if the water's not running, then the prompt of Linus getting a drink isn't happening. That follow-up. If that follow-up's not occurring, then the initial condition is not being met. So those two are logically equivalent. Then we got contrapositive. If not Q, then not P. So if Linus is not getting a drink, then the water is not running. Okay, so if Linus is not getting a drink, then the water's not running. That was logically equivalent to the conditional. Remember, the conditional, the prompt would be the water running, follow-up would be Linus getting a drink. But if we observe that Linus isn't getting a drink, then apparently the prompt of the water running didn't happen. So that's the conditional and the contrapositive go together. They're logically equivalent. Alright, so you've got a little bit of memorization to do in this section. Make sure you know De Morgan's laws. Make sure you know those other equivalences we went over with conditional, disjunction, negation of conditional, and conjunction. Also make sure you know these variations: conditional, converse, inverse, contrapositive. And practice the problems where you're having to, write things in words and flip things around. Because these mental practices here are going to help you in the next lesson, where you start examining arguments and trying to decide whether arguments are valid or invalid. Next two sections, we're going to be looking at symbolic arguments and then syllogistic arguments. So I look forward to seeing you there, and happy practicing.